Monday of week 6. Wow. Fantastic. That usually hints that week 7 is next week. Things that are happening in week 7. We have class scheduled at this time, Monday, Wednesday, and Friday of week 7 next week. But our lab session in the afternoon, starting at 1:55, 2 o'clock, a week from today will be our first written get-together. So we're going to have a midterm exam next Monday. I do have an exam, sort of a study guide for us to talk about, and we'll be reviewing that over the next couple sessions. It's not that we're going to have a week-long review. It's just that now that we've seen a lot of different parts, you guys realize that I'm a huge proponent of the I in ISBT. I love the integration part of it, and sometimes it takes us a while to get all the parts out in the open and to see all the parts and to get some experience with the parts before we can start to let it sink in how they integrate inside there. So we will be talking about things that will be integrating the topics we've been talking about so far, first 5 weeks and now in week 6, so that we're ready to go next Monday. We do have lab this afternoon. It's not an exam. It's another working with the electronics exam. This electronic equipment this afternoon. So we'll do that this afternoon. What I wanted to do is to finish up our conversation. Turns out to be chapter 2 in the text. Again, I keep on saying the text is not a mandatory thing to do. We're definitely covering it. But if you did happen to get a hold of the text, we've been talking about chapter 2 for a little bit, and we've been talking about it as a Prezi. And again, this is the way to find it. If you go to our home page in Canvas, it's down here. I have these little Prezi in brackets, but you know it's one of the presentations we did. This is number 2. When you click on that, it gets you over here to Prezi, the same Prezi that I'm using, and it's here. Open this back up. One of the things that we talked about all last week in talking about this Prezi was running through these 5 different characteristics of a purposeful, multi-minded system. And again, 5 is not a magical number. It just happens to be what the author has put it together through. And I believe we've made it as far as emergent property. We saw a little video. If you didn't get a chance to see it, I encourage you to look at it. The reason why I enjoy watching videos is 1, I don't do anything, I just stand here and watch it with you. But 2, you get to hear the vocabulary of systems thinking and the vocabulary of the types of stuff we're talking about from another human being. Okay? It's just the way Dr. Beaver puts it. It's all about how we do it in this class. But outside ISBT111, I'm not really sure how useful this is or if anybody else talks that way. So one of the reasons why I enjoy looking at some of these videos is that I grab, most of them are professors at other universities. Many of them are professors who have written books. This is their sort of role in life is to write business how-to books on the topic of systems thinking, just like this professor down from the University of Pennsylvania down at Penn here. And we saw a little bit about emergent property last time from Professor Ian Somerville in a fantastic Northern Ireland accent. And of course, he liked to call this an emergent property, which is fantastic. But we call it an emergent property here in the States, at least here in Philadelphia. We also took some time. We didn't see I keep on saying that this is probably one of the most important concepts that we'll be covering in this class. There'll be several, but this is one I really like to talk about. I really like to test about. This idea, I know it's complex, but it embodies so much of what we're talking about inside this class. I don't know how often you find this in other classes. I'm sure, I know I hear it on the radio all the time, especially as we're slogging through this goofy presidential election. I'm not a politician, I'm a scientist. So I enjoy politics as a spectator sport, but I keep on hearing all these either or. arguments. We have to do it this way, but if we do it their way, we're all going to die. You're either with us or you're against us. You're either for humans being alive or you're for humans being killed and slaughtered. It doesn't sound like a very productive conversation, but it happens to be a very productive way of beating your political opponent over the head with just goofy, non-sequitur arguments. And what that does, we saw, as I took the time with the pens last week, we drew this sort of number line up here between having one tendency, the positive tendency on one side, and the negative tendency on the other side, and then onto that, we placed art and science. Even at LaSalle, making it local, making it close here, we are the School of Arts and Sciences, and some folks who are scientists and some folks who are artists, they don't get the big picture. It's not everybody. But, sometimes they think, I don't know why I'm in the School of Arts and Sciences. We'll just have the artists play in their sandbox. We'll have the scientists play in their sandbox, and we just won't have too many mixers. There'll probably be fist fights that break out. That's not how it happens. Obviously, we need both. And the way to look at it is to look at things as we're scientists. At least we think we consider ourselves a scientific major. We have no problem looking at this as a graph with an x-axis this way, a y-axis this way, sort of the origin down here. So low to high, but we can talk about art and science at the same time. That's a big conversation. It's something that we definitely talk about inside ISBT because we like to integrate both of these ways of thinking about things. And yeah, I keep on throwing our name around. That's what we do. We then talked about emergent properties. We saw like a 10-minute video from Professor Somerville who mentioned that when you are talking about a system, you can look at the parts. We've looked at plenty of parts. We looked at batteries. We looked at wires. We've looked at resistors. We looked at diodes. We looked at Zener diodes. Now we've looked at operational amplifiers. We have lots of parts. It's when the parts get together and they start interacting that the cool stuff happens. That's the magic that happens. When a team goes ahead and plays a game or has a meet, when the team and the individual players each do their own parts, sometimes they play off of each other, sometimes there's a team leader. It's awesome when the team does well and you win, okay? But that's an emergent property. You can't win as a team unless all the parts are playing at the same time. And again, this is also one of these days when they finally kick me out of here, I'll write this lovely 8,000-page book on just this one topic of why it's important to keep on doing what you're doing. I don't know why she doesn't love me anymore. I haven't said hi to her for 15 years, and we just sort of stopped. I'm not sure why I'm not happy anymore. I used to like to, do all kinds of cool stuff, and now I don't do that. These things, these emergent properties, please define life. Please define love. Please define happiness. Please define success. The way that we define all of those things in integrated science, business, and technology and systems thinking is that they are emergent properties of a system. That requires that you have parts, and the parts are interacting, and they're interacting in the appropriate fashion. Not to be the correct fashion or the best fashion, but at least they're interacting in an appropriate fashion so that the system can go ahead and start spitting these things out as a byproduct. So happiness, it's a concept. You can't hold it in your hand, but you have to do something in order to be happy. You can't just sit there and be quiet and be happy. Maybe just, I said be quiet, maybe being quiet causes you to be happy. But you have to be quiet. There's this B word again. You have to do something, even if you're not doing anything. Crazy philosophical concepts, really, really high. This is why I keep on saying that other universities like to hold off integrated programs like ISBT until the master's level, but I know you guys can handle it. So we saw this little video from Ian Somerville. We're not going to see it now. I'm going to go past it as soon as I get past this guy over here. So, counterintuitiveness, our last topic of this chapter, then we'll leave it alone. So if you are an intuitive person, usually what that means is you watch the behavior of a system, you watch the behavior of the first innings of a game, or you watch how your team has been playing all season, and then you sort of have a gut feeling as to how they're going to do with the next time they're out. Okay, that's intuition. How did you predict that? Well, I just had an intuition. I can't tell you what calculation I used, or I can't show you the actual formula, but I just knew that would happen. Watching something on TV or watching a reality TV show, I just knew they were going to get together, or I just knew they were going to fall apart. That's intuitiveness. However, if you're intuitive, and that's great to be intuitive, and there's a lot of wins, every once in a while we get it wrong. And we have outputs from the systems, emergent properties, that are counterintuitive, meaning that no one expected that. Sometimes the counterintuitiveness is bad, hopefully not. Didn't expect that building to not be a very good building. Sometimes they're very surprising. Sometimes we talk about happy accidents in the lab, and also we invent a new product. So here's the problem. Success in playing the game changes the game. Let's talk about that. We talked about Henry Ford changing the game of being able to make an assembly line, so they were very successful in doing that. But now it changes the game. Now it was no longer how many cars can you make. The game sort of changed into what color can I get it in? Can I get 27-inch rims on it? Can I get some spoilers on the back? Whatever you want. So even though you may be a fantastic game player, tenacity, or staying determinism to play the old game, that'll convert success into failure. So that usually happens when you have these big companies that were great. Not going to drop the Apple word, but I accidentally dropped the Apple word. Apple seems to be the place that we pick on recently. Yes, we lost Steve Jobs to pancreatic cancer, but sometimes the success that you have in the past, if you don't keep on having that success because it's a emergent property, then you just sort of sit on your laurels and it turns into failure. As far as being a business person, again, this is a business book. This market economy, they usually only make rational choices. You can only get people to be excited about your product for so long. It depends on how much stuff you throw at it, marketing-wise. And this guy here, we're going to be studying this a little bit longer, a little bit later into the semester. Different events that happen, either depending on the scale, local or global. Sometimes they take a while to sort of ring out or have an effect on what you're doing. So sometimes, obviously, I think you guys have already studied, especially maybe in Business 100. Did you guys study the Tylenol scare back in the day before we had product safety labeling stuff? Of course, that was an immediate response. Obviously, we're talking about it as an academic exercise. The attack on the United States in September 11, 2001, that had an immediate response. There are other things that sort of have response that happens later on, and if you don't know where that response came from, you can sort of think that maybe that response was counterintuitive because no one saw it before. Okay? So some more words about counterintuitive, just trying to explain what it is and how the author explains it. Even if you do find something that's hurting you personally or hurting your business, even though you fix it, it may not make everything awesome the next day. It might take a while to fix it as you go. Again, going back to Johnson & Johnson with Tylenol, they went ahead and started this entire industry of making their products safe. It took a while for people to come back. It took a while for customers to come back. It didn't instantly. People weren't amazingly happy with taking Tylenol after people were affected by it. Let's see here. However, because of varying degrees of interaction between chance and choice escapes the boredom of predictability. Gosh, this is a lot of gobbledygook. What it means is, even though you may have a very strong intuition, sometimes things are just random. Let me summarize the second bullet point. Shit happens. You may not know what the shit is, and you may be surprised when the shit happens. But you could be planning something all month, or all year, or for 6 months, and then something happens outside your control that completely destroys your plans. It just happens to be what it is. You can't really plan everything that you want to do. Okay. So that was the topic of counterintuitiveness. We'll be talking about counterintuitive more as we go throughout the semester. I have one more little tiny video. Another sort of a pretty famous guy, Peter Sang is his name. He wrote a whole bunch of books sort of like this. Is a well-known author. And again, the reason why I like to throw this up here is we have another person talking this goofy speak, and hopefully because you understand the language, we get a chance to hear somebody talking fluently about systems. So not to make a really horrible analogy, but if this was an Italian class, after we learned a whole bunch of vocabulary, I'd hope that we'd see a native Italian speaker speaking Italian, so you could say, oh, I get what they're saying because I speak Italian now. Same thing with systems thinking. It's sort of it's a language. You can speak systems thinking using different human languages, but it turns out that he's speaking English, obviously. But if you don't know systems thinking, it might sound like gobbledygook because you don't know what the vocabulary is. So give us a chance to listen to Peter here, and then we'll finish up these videos. So he's an MIT guy.
Systems thinking is really a mixed bag, and I use it very, very cautiously. First, both words are problematic, but the word system is the most problematic, because if you say the word system, the picture image that pops up in most people's head is computer system. Like, we need a systems expert here because our system's not working. The second most common association is management control system, as it's not my fault, it's the stupid system. Right? So these are the two associations that come first to people, and neither of them is what we're trying to help people understand. So whenever I'm trying to help people understand what this word system means, I usually start off by saying, are you part of a family? Everybody is part of a family. Have you ever been seen in a family people producing consequences in the family, how people act, how people feel, that aren't what anybody intends? How does that happen? Well, then people can tell their stories and think about it, but that then grounds people in not the jargon, system or systems thinking, but the reality that we live in webs of interdependence. A family is a fairly close-knit one. You can kind of see most all the key players. But still, even though we can identify maybe on a list of 10 or 15 names, here's all the key people in my immediate family. Still, the complexity of interactions amongst all those people is obviously such that consistently families produce outcomes that nobody wants, which is the other kind of, you might say, fundamental rationale for all of this. It's not to, quote, understand systems. That's an abstraction. It's to understand how it is that the problems that are the most vexing and difficult and intransigent that we all deal with come about. And obviously, to get a perspective on those problems that gives us some leverage and some insight as to what we might do differently. Now, when you ask, what does it take in a business context for people to start to discern non-obvious areas of leverage? The answer is a very deep and persistent commitment to real learning. And there's a couple of features of this kind of deep commitment to learning. One is I have to be prepared to be wrong. Again, if it was pretty obvious what needed to be done, we'd already be doing it. So I'm part of the problem, almost for sure. My own way of seeing things, my own sense of where there's leverage is probably part of the problem. This is the domain we've always called mental models. If I'm not prepared to challenge my own mental models, the likelihood of finding non-obvious areas of high leverage is very low. Secondly, you need to really triangulate. You need to get different people from different points of view who are seeing different parts of the system to come together and collectively start to see something that individually none of them see. And thirdly, you need to be prepared that when you do start to see an area of relatively high leverage, it may take some time to develop, adopt, and apply really alternative behaviors and approaches. It may be years before a relatively higher leverage approach really bears fruit. Intelligence is always about systems. It's one of the reasons we don't really even need terms like systems thinking. You can say, well, show me an example where people have acted really intelligently. And almost always the examples will have to do with balancing the short term and the long term. They'll have to do with some ability to forego short-term benefits in the sake of investing in something in the long term. They're not just about opportunism and getting the most we can in the shortest period of time. Almost never will people give examples like that and say, oh yeah, I was part of a team. There was real collective intelligence in that team. That's the other thing to me that's very important about the notion of intelligence or smart in a social context. We all probably spend too much time thinking about smart individuals. It's one of the problems with school. It's very individualistic, very much about the smart kid and the dumb kids. Okay, and that's not the kind of smartness we need. The smartness we need is collective. We need cities that work differently. We need, industrial sectors that work differently. We need value chains and supply chains that are managed from the beginning to the end to really produce social, ecological, and economic well-being. That's the concept of intelligence we need, and it will never be achieved by a handful of smart individuals. It's not about the smartest guys in the room. It's about what we can do collectively. So the intelligence that matters is going to be collective intelligence, and that's the concept of smart that I think will really tell the tale.
That was obviously sponsored by IBM, presented by IBM. Peter Singh doesn't work for IBM. He's a professor at MIT. Any comments other than just being business gobbledygook? Does it have any relation to what we're talking about here? Or did I just pick a random video? No one wants to say anything. You want to say something?
Yeah.
Yeah. What do you think?
So why don't we? So regarding what he says about cities working together to find a common goal,
Right.
why don't we have scientists that can work together and can develop a more effective strategy to cure cancers and like stuff like that?
And that's happening. That really is happening a lot.
No, it's not.
It's not happening. It needs to happen more. No. I'm with. Oh, I'm on your team. It needs to happen more.
Right.
But it is happening. The reason why I say it's happening is because in ISBT, of course, we keep on picking those teams who are examples of what we think everybody should be doing, and saying, look at this team, look at this team, look at this team. They're doing such great work, and then you can find all these other examples where people are just trained to be doers. Don't copy, don't cheat, don't look at anybody else. Be the smartest person in the room.
Right.
That old story of, when you go to college, your professor's going to say, look at everybody in the room, look to your right, look to your left. One of those people isn't going to be here because I'm going to fail you. I mean, that's sort of a standard Hollywood college. We just let the smart people go through, and no one else has any value to solving the problem. Obviously, that's crap. Everybody has different experiences. We constantly talk about asking people to look at a problem from different directions. This integration again. But yeah, I agree with you. I don't think it is the average to have working collaborative teams, but my hope is that everyone can get more get that way.
Well, you do have to have a group of people who actually work together, and then you can better find a solution to a problem. So if scientists were to work together, so for instance, let's assume that a biomarker doesn't work.
Okay.
And then if the scientists were to publish that and to say to the other scientists, hey, this biomarker does not work, so can we try something? So can we try something else? And
Sure.
that way we can better spend our research.
Exactly. So layered on top of that is this competitive idea that my company and your company are in competition.
Right.
And if you find out that this doesn't work, like, look at those guys, they're still trying it the wrong way. We're going to beat the pants off of them. It turns out I do not have much experience or any experience in the pharmaceutical area. I have a little bit of experience in the automotive area. Yeah, people talking about Ford. I didn't work as a Ford employee, but I worked as a contractor for Ford. So when I would go to Dearborn, Michigan, now this is back when we had 3 car companies in Michigan. They've since 2007, they've all gone away. This is back in the 90s. But the Ford employees and the Chrysler employees and the General Motors employees, all three of those competing companies had their headquarters within a 10-mile radius. And all the engineers, they would go to TGI Fridays for lunch. And when the engineers were there for lunch, it didn't matter what badge you were wearing. They were engineers first. Hey, Bruce, what are you working on? Well, Gary, this damn thing won't work. Oh, we figured that out last week. Here, have this. So you're talking about all this corporate espionage of they collaborated like crazy. And so when you think like all the American car companies look exactly the same, that's the reason why. Is because all of the headquarters and all of their engineers were in the same city. I mean, all their kids played on the same little league because they all lived and worked together. So in that case, it wasn't at the company; it was their employees that were moving things back and forth. But yeah, so I don't know. I don't know if that's a good thing or a bad thing.
Well, it's a good thing in the sense that you can actually find a cure to a disease, but it's not but it's a bad thing for a corporation.
Right, exactly. Especially if the sign. So that's why we invented non-disclosure agreements.
Yep.
So even though you're going to have lunch with Bruce, Gary, you can't tell him that we solved this because I have your signature here. And if we find out that you're the leak, we're going to lose your job. So yeah, there it is. Any other takeaways from this? I'll ask the question. Is it any way related to the stuff that we're talking about in this class? Did you understand what he was saying? Again, no one's not smart. I'm just asking vocabulary-wise. It was sort of, he was using the words that we were talking about, which I thought was pretty cool. Okay. All right. So again, you can go. I'll be right back. These are the things that we talked about for this particular chapter. Again, openness is, it's all integrated. It's all depending on openness is the willingness to accept new information and share your information when you're done. Purposefulness, we are talking about people as parts, people as of components. You have to give them a reason to do their job well. The multidimensionality was that plot I keep on harping about. The emergent property, the success or failure, only comes about after the system is working and functioning. And then this counterintuitiveness is, I guess another way to summarize this up, not that the other folks didn't do a fantastic job. If there was no counterintuitiveness, how about the other phrase? Everybody ever heard the term unintended consequences? Okay? If there was no counterintuitiveness and there was no unintended consequences, then we'd never have any problems to solve. No, cancer's outside our job, but we wouldn't create problems. So you can think, well, the people who create problems are just evil. They're out there just creating problems. They're creating problems of student debt, and they're creating problems of not enough housing, and they're creating problems of not enough clean water. Those problems, I believe, unless I'm wrong, I don't think there's a secret organization of bad people that are making these problems for humans. They've just come about because we've solved other good problems, and when we solve other problems, sometimes they have unintended consequences, and that can also be described as counterintuitiveness. So as problem solvers, why do we need to fix this in the first place? As problem solvers, sometimes we need to figure out where the problem came from, and sometimes the reason we have a problem now is because we did so great before. It was a success that caused the problem now. Now that gasoline is so inexpensive and now below $2, maybe more people are buying it, and maybe now we can't supply the gasoline fast enough. I'm just making this up. I haven't seen any gas line. But if that were the case, then we've created a problem because gasoline is so required. We talked about the PS whatever, PS2, PS3, PS4. Every time Sony announced a new PS, there's not enough of them. People show up at Walmart or Toys R Us and they start fighting over the 10 that are available. Where's the rest of them? They created a problem, not because, again, you can think nefariously and say, did they by design not make enough to cause this? I would think that it's probably not the case. They would love to sell these things because then more people get bonuses and raises because their software and their games are fantastic. But because everybody wants it and they were not able to make things fast enough, it was sort of counterintuitive. The problem of not being able to meet demand with supply.
Right, but if they don't actually raise the prices, they can increase the supply and demand chain.
So now we look at all the so you're suggesting that we could just use good old economics and just do supply and demand, just make them $1,000 a piece.
And if you have less production of something,
Yes.
when you have massive production of something, people will buy it more actually.
Yeah, so
They feel left out basically.
right, that's why we have economists to try to solve that. Not saying your answer is not right, but but it still happens anyway, unfortunately. So even though they're like this is a classic or a textbook example of what went wrong, they still need to solve it. Maybe it's thankfully why we don't have everybody investing on the stock market and everybody making wins every day. We'd like to see people gamble and win, but the stock market is just like that as well. The stock market is sort of chaotic, it's sort of random.
Actually, if you live let's say like about $20,000 in there for 25 years, you can actually get a return of $2 billion.
Oh, just leaving it put, not playing it maybe long term.
Because the dividends will increase and keep increasing. So by 25 years, you will have enough money to retire.
Fabulous idea. We should just do that.
Well,
Everyone does that.
We should, but we don't, unfortunately. 2, 3. So this is a conversation starter that I'm handing out, not a conversation ender. We're going to spend a little bit more time with the operational amplifier this afternoon. So this is, again, we don't have a textbook, but if we were to write a textbook and write down in the table of contents what we would have covered the first 5 or 6 weeks, I think these topics would show up. Okay, so this is just hopefully that if you've been taking notes, this sort of paralyzes, wrong word, it's a Freudian slip, parallels your notes. Okay, so as we walk down memory lane here, hopefully this, we talked about that. Was it 5 weeks ago when we started talking about the idea of a system, open and closed, and natural versus human-made? We had to start somewhere, right? So I will be asking you, and again, this is sort of a study guide for our exam. I will be asking you to go through this little tiny elementary exercise. Yes, I know you guys already get it because we're talking about really high-level stuff. So in order to talk about the high-level stuff, I know you already understand the low-level stuff. So that's why this is a gimme. Like, here, can you do this really simple stuff, hit the points, and then we'll move on. So yeah. And secondly, talking about the exam, you guys already know it's open notes, open study guide, open phones, open laptops, open computers, just not open person next to you. I'd like, in the time that we have, I'd like to hear your thoughts in answering the questions. I would not like a collaborative answer. My 200 level classes, we have collaborative answers, but for here, I'd like to hear your answer. But I'm not going to take away any tools that you might use. So if you want to fill this with any notes, if you want to download whatever you want to your phone or your laptop or your tablet, or if we're going to be taking it in the lab downstairs, so if you want to get there early and make sure you grab one of the computers, that's fine too. If you just want to study for it as a traditional exam and just come in, bust it out and leave, I'm sure you'll do fine that way too. You don't need all the other tools in order to solve it. I would never dream of asking you on the exam, go to this website, and not everybody will bring a computer along. But I don't want to turn off your electronic devices. You can have that. But anyway, I may ask you, or I will ask you, to answer these questions for a system. I'll throw a system up there and ask you to describe it exactly these terms, so that I can sort of assess and make sure you guys understand the difference between natural, human-made, physical, conceptual, static, dynamic, closed, open. Pretty obvious. What does it mean to have system with input. What does it mean to have a system with output? We've talked about those three primary flavors of inputs and outputs, being material, energy, and information. Again, in any order: energy, information, and material. Information, material, energy, however you want to say it. For all three, they're all pretty much equivalent. And then talking about the process being the instructions of how this system works, or at least by design, or maybe going back in and finding out how it really works by doing an analysis. There's our picture. This is the tattoo that everybody should get somewhere on their body. The picture of the box. This is what we're talking about all 4 years. Input, output, process inside the box, and environment outside the box. As in taken as a whole, that's our system. We spent some time talking about systems. We then spent the last few weeks talking about electronics as an example of a system, so that we can look to see what it takes to put the components together, so that we can point to input, point to output, point to process, point to environment, and say, hey, look, I've built a system in the lab. I've drawn a system on the board. I can go ahead and comment on how well it's working. The components, the things that we've been talking about, electronics: voltage, potential difference; current, the flow of something; resistance in units of ohms; and then we introduced this fantastically awesome, powerful thing, Ohm's law, where these are how these three things are related: V equals IR. We then talked about batteries, and we've talked about batteries as a component. We've talked about batteries as balloons. We've talked about batteries as a component. So if you look at this thing in system speak, as you know, there's our battery. It's just a box. Conceptually, it's a box. It could be any flavor you want. It could be a AA battery. It could be a car battery. Somehow, the battery senses how much resistance it is pushing against. So that's why I have it as an input. Of course, it's sort of like, if my job was a human battery, I would like to flow electrons out, but I can only flow the electrons out as fast as I can push them against a resistance. So the battery, we can go through all the physics, senses how much resistance there is, and then depending on the resistance, the battery has a certain push, and then that results in a certain flow. So this is exactly V equals IR, or in this case, we resolve it, I equals V over R. The V is the push inside the battery, the resistance, the R, is what the battery senses, and the current is what it produces. Okay? We know that that is the reason why we have batteries, is to flow electrons through the system. The resistor as a system, here comes the current. The flow is going to go through the resistor. The resistor, of course, knows its own resistance, or maybe if it's a variable resistor, it knows its own resistance because light is shining on it, or the temperature has changed. And then out the other side comes more current, and then also potential drop. The push slows down. We've already measured that. We've measured the voltage between A and B, and then we've measured the voltage between V, B, and C, and we solved the voltage change dropwise. The equation happens to be exactly Ohm's law, and that's why we use the units of ohms for resistors, because this is what Friedrich Ohm based his law on, was the law of resistors. We then got some equations. We haven't gotten too crazy about doing math. We talked about resistors in series together, resistors in parallel, how to calculate their resistance. When they're in series, they add up, the resistance gets higher. When they're in parallel, they add 1 over, resistance goes down. We talked about dividing the voltage up between the resistors. We've measured that, voltage from A to B, voltage from B to C, voltage from C to D. And then also we've had current divider equations where we split the current because of parallel. We had a little talk about diodes, why diodes do what they do in the first place. We know about diodes that are forward biased, they allow current to flow. Reverse biased, which is facing the wrong direction, they stop it. A Zener diode does both. It stops it until you push hard enough, and it lets it flow. And then we spent a little bit of time talking about that periodic table of the elements and talking about semiconductors, silicon, germanium, arsenic, antimony, and indium.
So basically, we just have to define them.
Yeah, I just want you to know what they are. It's a life itself is a vocabulary test, right? It's a vocabulary exam. The thing that we are spending more time on in lab this afternoon are operational amplifiers, and we'll be spending a deeper amount of time with op amps, operational amplifiers on Wednesday and Friday. So that's this stuff here. We'll be talking about that this week. And then we just finished talking about chapter 2. Chapter 1, there's a Prezio in chapter 1. Chapter 2, we just talk about these 5 guys. And then that places us at the end of the first half. Is this a small amount of stuff or a large amount of stuff? I'm sorry? It's pretty damn small. However, if you wanted to write a book about just these topics, could you write one? You could write many, many books. Yes, actually. So the topics we're talking about are short and sweet, but it depends on how deep you choose to dive into any one of these topics. We're going to try to keep it up here at the top as we go. Fantastic. I will see you guys in a little bit.